August 25th. It is absolutely one of the most phenomenal dates in all of math history. So let's jump right into this explainer. Following the script structure outlined in our source document ENGV, we're going to explore this single, truly golden day. A day that literally, and I mean secretly, built the entire modern world we're living in right now.
Right, so what's so crazy about August 25th? Well, across entirely different centuries and completely different countries, brilliant minds who were either born or who passed away on this exact calendar day completely revolutionized our everyday lives. Seriously, it's almost as if the universe just picked this one specific date to drop these massive upgrades to human knowledge. Let's meet the people behind these upgrades one by one.
Looking at our timeline here, stretching from 1561 all the way to 1964, we're going to meet four incredible mathematical detectives. We'll trace their lives and see exactly how their mind-bending discoveries on this very day shaped the tech that, let's be honest, we completely take for granted today.
Okay, let's kick things off with a very modern mystery. Have you ever wondered how our GPS apps know exactly where satellites and planets are in the sheer vastness of space? I mean, when you pull up a map on your phone to find the nearest coffee shop, how does that tiny device pinpoint your exact location using a satellite zooming around the Earth at thousands of miles per hour? It kind of feels like magic, doesn't it?
Well, the answer takes us all the way back to August 25th, 1561, with the birth of our astronomy table master, Philip van Lansberge.
Now, Philip van Lansberge wasn't writing computer code. He was doing something much, much more grueling. He spent his life advancing the study of spherical geometry and doing the exhaustive, painstaking work of constructing precise mathematical tables of sines, tangents, and secants. If you're wondering what that actually means, think of it as writing the world's very first hyper-accurate mathematical dictionary of curves and spheres. Before computers existed, if you wanted to know how an object moved in an arc across the sky, you had to calculate it by hand using his tables. His work was so phenomenally accurate that the legendary astronomer Johannes Kepler actually used Philip's exact tables to map out the orbits of our universe. Kepler literally tracked the planets using Philip's math. Today, we use those exact same foundational geometric principles every single time our smartphone connects to a satellite overhead to triangulate its position and give us turn-by-turn directions.
So the absolutely crucial point here is this. Every time we map the stars, we are essentially reading his tables. Whether it's a telescope peering into deep space or a GPS unit guiding your car, we are secretly relying on his 16th century geometry to navigate our modern world.
Still on August 25th, we're jumping ahead over 100 years, moving from 1561 to 1699 to uncover our next mystery. Same date, different century, and an entirely different mathematical puzzle waiting to be solved. Think about the machines around you for a second. Why do the intricate physical gears in our mechanical watches or the heavy steel gears inside a car engine interlock perfectly without ever grinding, stripping, or getting stuck? How do those metal teeth spin so flawlessly day after day, year after year, without destroying each other in a shower of sparks?
That brings us to August 25th, 1699, and the birth of Charles-Etienne Camus, a man who became the absolute master of gears.
Camus did something truly extraordinary. He looked at abstract geometry, the kind of pure conceptual math you might see scribbled on a university chalkboard, and he brought it squarely into the physical world. He applied those abstract geometric formulas directly to hard, heavy physical machinery. Before Camus, engineers were basically just guessing at how gears should fit together, which, as you can imagine, led to a lot of broken machines and jammed wheels. But Camus figured out the exact, flawless mathematics needed to design perfectly interlocking toothed wheels. He calculated the precise curves and angles required for gear teeth to push against each other with maximum efficiency and zero binding. Because he solved the complex math of how circles and teeth should seamlessly mesh together, we enjoy smooth shifting cars, perfectly ticking watches, and efficient industrial machinery today.
The big takeaway here is that every single machine you use is secretly driven by math. The smooth, reliable mechanics of almost every engine or clockwork device we rely on today owes a massive, invisible debt to him.
Let's move along our timeline. We're going to jump ahead again, this time to the year 1867. One date, so many incredible stories. Let's see how another massive shift in human history occurred on this exact same day.
Consider this for a moment. How does invisible energy flow through miles of solid copper wires to charge our smartphones, power our screens, and light up our entire cities at night? Where does that invisible, seemingly magical power actually come from, and how in the world did we learn to harness it?
On August 25, 1867, we lost the pioneer of power, Michael Faraday.
Faraday's story is one of the most incredible in all of science. He didn't start out in elite academic circles or prestigious universities. No, he began as a humble, deeply curious bookbinder. He would literally read the science books he was binding during his day job. But he was relentless. He pursued and ultimately decoded the invisible laws of physics governing electricity and electromagnetism. He ran hundreds of experiments until he discovered electromagnetic induction. Put simply, he figured out how to turn the physical movement of a magnet into a steady electrical current. Just take a second to appreciate that. The very fact that we have electricity powering our homes, our appliances, our life-saving medical devices, and even the very servers hosting this explainer is because a bookbinder figured out the mathematical and physical relationship between magnets and electricity.
As he so beautifully put it, nothing is too wonderful to be true if it be consistent with the laws of nature. He showed us that the natural, mathematical laws of our universe are where the real magic actually happens.
Fast forward to 1964. A completely different century, a completely modern era, but the very same date brings our most mind-bending mystery yet. Let's look at the final dot on our timeline.
How do modern physicists make sense of the invisible, hyper-complex tangles and strings that make up the quantum fabric of reality? When we dive deep down into the subatomic microscopic building blocks of our universe, how do we possibly begin to understand that level of chaos?
Enter Maxim Kontsevich, born August 25, 1964. He's the brilliant mind widely known as the quantum knot weaver.
Kontsevich tackled some of the most daunting math in modern physics. He helped us unravel what is known as two-dimensional quantum gravity by mathematically untangling something called the Vasilev invariance of knots. Actually, scratch that, just saying the name makes it sound impossible. Think of it more like trying to perfectly untangle the most incredibly complicated microscopic ball of string imaginable, where every single loop and knot holds the secrets of the universe. By merging high-level abstract algebra with physical string theory, Kontsevich basically found a mathematical rulebook to decode these quantum knots. He created a framework that allows physicists to map out these complex theoretical tangles without losing their minds. Thanks to his sheer mathematical genius, we're getting closer to understanding the fundamental, structural nature of reality itself.
His work beautifully proves our next big point. Even the most chaotic tangles in the universe hide perfect mathematical patterns waiting to be found. It looks like pure chaos, right up until you find the math.
So, looking back at our completed timeline, we can trace a remarkable path, from Lansberge mapping the stars in 1561, to Camus perfecting physical machinery in 1699, to Faraday harnessing electricity in 1867, and Kontsevich decoding quantum knots in 1964. We can see how all these remarkably brilliant minds are forever connected by this one golden day.
But what really connected them all? Every person we met today, across different centuries, different countries, and entirely different scientific fields, all fundamentally asked the exact same question. What is the logical pattern hiding inside the chaos of the natural world? And because they dared to ask that question and did the grueling work to answer it, our world today has GPS, perfectly interlocking engines, global electricity, and a much deeper understanding of the quantum realm.
Because they found those hidden patterns, our modern world works effortlessly. It leaves us with one final, provocative thought to take away from this explainer. What pattern will